Yeah, I hope my screen is visible. Yeah. So thank you, Anjali. So now, as she told you, I guess I've unmuted myself. Yeah. Yeah. So as Anjali, as you have given a beautiful description of how kernels work. So if you have the question, why we are using kernels, and like what is the purpose of that, and like how are we even getting like okay, she has explained you how we're getting a new image, but like why do we even need a new image? Like why we are taking the current image using a kernel and taking the second image and working on it. We'll cover that. Don't worry. So firstly, again, to back to the basics. So types of neural networks. So like if you look at the different types of neural networks, like there are a lot of different types of neural networks actually. But for the scope of this fest, we just have three. One is that I've already learned yesterday, and that is the artificial neural networks or the multi-layer perceptrons. Everything that was taught today is comes under this, and the term multi-layer perceptron, which you might not have heard, is for the same thing. Then recurrent neural networks. Anjali has told you that we are going to cover this in the afternoon. But just a brief description of what it is. It is a tool with the help of which you can develop something. We can develop something called like an NLP. What is NLP? It is natural language processing with the help of which you can develop your own Google Assistant, your own Alexa, or even own Jarvis, if I want to elaborate. So yeah, that's the thing. And then, but the topic of focus is convolutional neural networks. That I'm going to be considering now. So moving on. So what is a convolutional neural network or a CNN for short? For short. So to answer that, I guess we should just ask ourselves, ki, okay, what convolutions are? And if I were a dictionary, I just tell you, okay, convolutions are a mathematical interpretation of two functions to give us and one output function. But what does that mean? It simply means that it's, in simple terms, like we take two different functions, as I've mentioned in the description, like we take an input image. For example, we have taken this cat. Let me take my pointer. We have taken this cat. Then we take a filter, as Anjali has mentioned, and then we get an output image that is what Anjali has showed in the previous website, like a vertical image or something. So that's the thing. So like convolution basically do that. And if you talk about similarities of how a convolution neural network is similar to what you have learned yesterday, I'll just go into that right now. So what I've learned yesterday, MLP again, multi-layer perceptron, what it was like. First you have an input layer, and then with the help of weights and biases, you get another second layer. We call it the hidden layer, and then with one more another pair of weights and biases, you get the output layer. And then again we back propagate, change the weights and biases, and then repeat the step again and again. And then you get how many, if you want to train it for how many epochs, and you do it for many times. And then yeah, that's how an MLP system works. Now coming into a CNN network, it is almost very much similar to an MLP network. But just that instead of neurons, what we have over here, here we are going to have images. Like all these square things are images. So like from a single image, we are going to use kernels to obtain more different images. And then within the new obtained images that we're going to have, we're again going to use different kernels to get one more layer of images. And then again, we're going to flatten and all that stuff. And then we'll let you know what exactly it does. And then we get an output layer again, then we back propagate, as I mentioned. And here, and yeah, so the basic difference is, as we had weights in a basic neural networks or in an MLP, we here have kernels. What kernels are Angela has told you, and each value in the kernel, like -1, 0, 1, it is not restricted that the value should be -1, 0, or 1. It can be any value that you want, but like those values are the weights in a CNN network. So yeah, so like just like in an MLP network, we backpropagate and we change the values inside the kernel, and then we repeat the steps again. That's how a CNN network works. And if you want to see how exactly, oh yeah, and this is like after CNN came into the picture, like the basic neural networks are like just thrown away. Like they were like, and like CNN just ruined the career in short. Yeah. So if you look how exactly a CNN network looks, and this is the visual representation. First, we have an input layer. Then we perform convolutional plus ReLU and max pooling in a single at a single time. What convolution is, what a ReLU does. I guess ReLU has been covered yesterday, so you might have a brief information regarding that, and max pooling. So don't worry, we have you covered. We have more trainers that will explain you how exactly that works. So yeah, so like if you just want to visualize how it looks, it's like this. So, like we have an large input image, and then finally we're gonna flatten that image into a one-dimensional photo. Why we do that, how we do that, we have covered. Don't worry. Moving on. Why should we use convolutional neural networks or CNN? First, that is time. So if I just would take you over here, yeah. If we look, if you have this image as an input image in the convolution network, then what is a neural network gonna do? What it's gonna do is it's gonna take your first layer of pixels, line it up with the second layer of pixels, and with the help of that, it's gonna get a large image. Like it's gonna get a large value. It's gonna get a large layers of neurons. So like I'll explain you what it does. Suppose, for example, consider that there is the previous image, or the 784 by 784 image. Okay, and if you do the mathematics, like I'm not good at math, but if you do the maths, thanks to the calculator, it told me we get around 6,14,000 neurons in this. We get 6 lakh neurons just in the first layer, and one dimension, obviously. And if you take more weights and biases, for example, you decide to take, okay, I want to take 100 weights. And if you just do the calculation, like I've done the calculation for you, don't worry, I guess I've got you covered. But if you just do the maths, you know, when I have one layer, I've like wapas, I'm using weights and biases, and then I'm going to the second layer with 6 lakh neurons in the first layer, then you know how much it approximates to. It's around, it's बहुत ज़्यादा. I hate my typing. It's बहुत ज़्यादा. Like for the international audience, it means it's a lot of neurons. Like if we just do a simple calculation of 6 lakh into 100, you're gonna get 60 million neurons. You're gonna 60 million parameters just for the second layer. And if you look at it, it's not feasible, right? 60 million neurons. It's not a joke or something, right? That's what. So like first is time. Like CNNs helps you a lot because it doesn't take your whole image and then aligns it side by side pixel. It keeps the image as it is. Second is accuracy. Now CNN is very accurate for images. Obviously, it's used for images. It can also be used for many different things, but we won't go into that. But yes, so why is CNN so accurate? First is CNN does parallel computing. So what's doing is like basically not basically we are gonna have a lot of layers. Like so we are gonna have, as I mentioned, your convolution layer, a ReLU, and a max pooling. All these layers in a single layer. So with the help of this, we are gonna reduce the image, and we are just gonna extract the main features from every image, and every kernel, every different kernel that we're gonna have in our network is gonna help us identify a different feature from our image. And also one more thing that I've talked about, like keeping the spatial integrity. What spatial integrity is integrity is like, as I mentioned, a basic neural network. What it's going to do is, if I have two layers, it's just going to take the second layer of pixels and line it up with the first layer of pixels. But if you do that, what's going to happen? Like for example, if you have this image, like the neural network will be like, bro, okay, so in the start, I have a lot of blue pixels, and then after that, okay, I have a yellow pixels, and then again I have a few blue pixels again at the end of the single layer of neuron of pixels. Then okay, so what the model will think, okay, so if I get anything that has a lot of blue pixels in the start, a bit yellow here and there, and again a lot of blue pixels in the end, then it's sunflower, right? So the model will like, okay, this is a sunflower. I'm very good at telling you what a sunflower is, but if you think, if I give him this image again, it has blue in the start, it has blue over here, and then again you have a yellow color in the center. Now tell me, is this a sunflower? No, it isn't. It is a Detective Pikachu, right? So, but a neural network will tell you that it is a sunflower because it will do the exact same thing that I've told you. It will look, okay, starting with a lot of blue pixels and with again blue pixels, and then you have yellow pixel in the start. But no, what a convolutional neural network will do is like it will look here. For example, the kernel is sitting right over here. Sorry, the kernel is sitting right over here. So what it's going to do is it will just look at the eye. It's like, okay, so what is above the eye? So above the eye, okay, there's something yellow in color. Again, left to the eye is yellow in color. Again, so what it's gonna do is if it takes a single kernel, if it takes a single pixel, it will look what is next to the pixel, what is up, below, left, and right to the pixel, and then it will try to understand, okay, how the object is. So if you look at the Pikachu again, what is going to realize, okay, if we take this eye to the left of the eye, we get another eye. If you come a bit left to the left bottom side, we get something, a nose and a mouth. So obviously the model doesn't know what a nose or a mouth is, but we can just see key, okay, to the left of the eye, to the left of this black pixel center, we're going to have again a yellow patch, and then again a black patch, and then again we should have something over here, and again we should have something over here. So that is what a convolution neural network is going to keep in mind. It's going to store what all pixels are next to your current pixel in focus, and it's going to work along with that. So yes, and spatial integrated I've talked about, yes. And then a deep architecture, as I've mentioned all this way, all this along. Okay, a single layer in a convolution neural network consists of convolutions, of max pooling and ReLU in between them. A ReLU or any other activation function that you want. You have learned yesterday what all you can use. So yeah, so with the help of that, we can get quite a deep architecture. And if you go to some pre-trained models developed by the top institutes like Google and all that stuff, you'll realize they have developed such a deep architecture of so many different layers, and what not. We can't even recreate those things. Like they are like these architectures can go to a next level. And yeah, so like one the most important thing that why we should be using CNN, why we should be learning convolution neural network is that it's quite a cool name, right? I love the name, yeah. So moving on. So yeah, so a basic example of CNN. So I guess yesterday we talked about the MNIST dataset. So the MNIST dataset also recreates something called of MNIST fashion dataset. So in that fashion dataset, what we have is many different pictures of many different fashion things. If you are quite into ML, you might have encountered this already. But yeah, so like here, just forget about what this dataset is. Just think about we have three different images. All of these three are a shoe. I know it's not that properly visible, but just bear with me. So yeah, so like if you look at this, we are using a different kernel for this, a different kernel for this, and a different kernel for this. And you can visualize over here that this kernel is good at finding out the rare part of the shoe. Okay, so this feature is a rare part of the shoe. This kernel is good at finding out the lace part of the shoe, and this kernel is good at finding out the heel part of the shoe. So if we have many such networks, if we have many such kernels applied to an image, for example, a shoe, so this can identify the rare part, this can identify the lace, this can identify the heel. And if you have many more different things which can identify the part where the circular part where we like from where we wear the shoe, the other parts to identify the sole, the other heel part, and all that stuff. So like with the help of this, if we have many such different feature recognizing kernels, then and if we add them all up together, we're gonna have one single model which can identify a shoe very easily. So that is the advantage of using convolutions, that you can have many different kernels identifying many different kinds of features, and then we add up all together to get a single thing. So yeah, that's all from my side.